Good. Here's the quotient ring that we defined last time. You give me a ring R and an ideal I, given two elements A and B in the ring. We say A is congruent to B mod I if A minus B is in I. This defines the equivalence relation in the ring on the ring R. The equivalence class of an element A is called the congruence class, also called the coset of A. By definition, it means all the B's in the ring that are related to A, so all the B's that are congruent to A mod I. The set is equal to all the elements of the form A plus X, where X varies over I, and we denote this set by A plus I. So A plus I is the coset of A, or the congruence class of A. R mod I denotes the set of all these congruence classes, or the set of all these cosets. We defined two binary operations, one called plus, one called dot, on this set R mod I. So the input would be two elements of R mod I, meaning two cosets, meaning two sets like this, and the output would again be a set like that. The definition is down here. Unnecessary to repeat it right now. What we want to repeat is this observation, how to work with these two operations. If you give me two elements of R mod I, they look like this: A plus I and C plus I, where A and C are some elements of R. And to add them, you just add the elements and take the coset of that sum. And similarly, if you give me a coset of A and a coset of C, then to multiply them, just multiply A and C and take the coset of that. That's how the addition and multiplication work. And we showed this theorem that with these two binary operations, we just defined, R mod I becomes a ring, and there's a surjective ring homomorphism from R to R mod I, taking an element A to the only thing that you can take it to, the coset of it, A plus I. This is called the quotient homomorphism. And R mod I is called the quotient ring. All right. So here are some remarks. A ring got to have a 0. The 0 of R mod I is, you guessed it, the coset of the 0 element. But that's same as I. In fact, note that A plus I is I for some A in R if and only if A is in I. This is a very easy exercise. Verify. Second, if R has an identity, then R mod I also has an identity. If R has an identity 1, then R mod I has an identity and it is the coset of the identity of R. Again, follows from this. You see, 1 plus I multiplied by some A plus I is 1 times A plus I, but that's just A plus I again. So this is an element of R mod I, which when you multiply by any coset, you get the same thing back. Okay. And then finally, if R is commutative, then so is R mod I. R mod I is also commutative. And to process all this, we should work through the definition that we have seen the definition when R is Z and I is an ideal n times Z. So probably we can work it out here. Make some space here. No. Maybe here. So example. So for R, we take Z. And you fix a natural number, 4, 7, 15, and take the ideal I to be all multiples of n, nz. So in this example, in this situation, what does A congruent to B mod I mean? It means that the difference is in I. That's the definition up here. Yeah, but the I is n times z. What does that say? That says that the difference is a multiple of n. That is, the difference of a and b is a multiple of n, meaning n divides a minus b. But if n divides a minus b, that's exactly when we write A is congruent to B mod n, if you recall. It just means that the difference is a multiple of n. So in this example, congruence mod I simply amounts to congruence mod n. So this congruence modulo n ideal is a generalization of this concept of congruence mod n. A rather big generalization, or a vast generalization. Okay. So in this example, the equivalence classes, these congruence classes, are exactly the congruence class mod n. So Z mod n is same as R mod I in this example. So in the present notation, Z mod n is denoted, how do we write this thing? The ring modulo the ideal. Yeah, so we'll use these two interchangeably. The notation Z mod n was anticipating this thing, Z mod nz. Yeah, so we can use either of them. And we have a quotient homomorphism. Pi from Z to Z mod n, taking an element, an integer k, to its corresponding coset, which we earlier used to denote like this. Yeah, so, and how does the addition and multiplication work? Maybe it's better to be even more specific. Take n equals 5 or something. And so we are considering Z mod 5Z. Yes. Take two things in Z mod 5Z. Here are two things, 17 and minus 4. What does 17 here mean? It means 17 plus 5Z. Or more explicitly, it means this set. 2, 7, 12, 17. That's it. Minus 3. Yeah. So you see, given a set does not necessarily mean that you have picked out an element. Yeah. But you can give it by picking an element. So here is one, here is another one. So minus 4 means minus 4 plus 7z, 4 plus 5z. meaning the set -4, 1, 6, etc. And to add these, what was the prescription? It said choose an element from this coset. Well, I choose 2. That's an element from this coset. And choose an element from this coset. Well, I choose, I don't know, 1. And I add them, 3, and take the coset of that. So it's going to be 3 plus, so the sum of these two things in Z mod 5 is going to be 3 plus 5Z, which means the set 3, 8, 13, 18, oops, am I doing it right? Yes, 23, etc. But where was this, what was this subtlety? The subtlety is that instead of choosing 2 and 1, you might have chosen, I don't know, 17 and 6. Instead of choosing A and C, you could have chosen A prime and C prime. And then, by adding them, you'll get 23. So you'll get 23 plus 5Z. But of course, that's exactly the same thing. See, take 23 and add all multiples of 5, you get exactly this set again. Yeah, so what you get here does not depend on which representatives you choose. And the same discussion holds for multiplication. Okay. So the general quotient construction and the addition and the multiplication that we defined on R mod I generalizes the construction of Z mod NZ and the addition and the multiplication that we had on Z mod NZ. And after we do the first isomorphism theorem next time, we'll give more examples of this. And this would actually lead to lots of interesting examples of new rings, examples of new fields, like we'll see that there is a unique finite field of order p to the n where p is a prime. And these are extremely important in coding theory and all sorts of things. In computer science, we'll also construct these finite dimensional extension fields of rational numbers. So fields that contain the rational numbers and are finite dimensional vector spaces over the rational numbers. And these fields, the finite extensions of Q, they're extremely important in solving polynomial equations, etc. So all that comes out of this quotient construction, and then looking at polynomial rings and stuff. Okay. So we'll do the first isomorphism theorem, talk a little bit about prime and maximal ideals, and then go back and do chapter 5, which is talking about the example of quotient construction for polynomial rings.